I mean, why even bother to ask this question? Why are we even interested in tabular reasoning capabilities of LLMs? I mean, we all know that LLMs are great or very interesting in terms of reasoning capabilities over natural text, but why do we even care about the tabular reasoning capabilities of LLMs? And the answer to that is pretty straightforward, because we already know that consumers and industry are already using LLMs in that capacity. We already see that LLMs are fed with tables and retrieval augmented generation pipelines, but also just in general, like people just hand over tables to large language models and ask them, hey, just general questions over their tabular data. So what we wondered is like, how good are LLMs actually at these tasks? Like, what are the risks there? How good do they perform? But to address this question, we first this question of how good LLMs are at tabular reasoning, we first had to answer that question: how can we even evaluate these LLMs? Because most evaluation metrics for large language models are built from a linguistics point of view, which we will also cover later. But for tabular reasoning, do those classical methods even make sense? Do they still produce valid results? And once we have the answer the first question, the second question that comes to mind is, well, using that method that works best, how robust are LLMs actually to real-world tables? Like, how are they performing against data that we just see in the real world? Yeah, and to start out, like, what kind of data set did we use to perform this test? I mean, obviously, if we want to test the tabular reasoning capabilities of large language models, we have to have a certain tabular data set. And for that, we used the TQA bench data set that was published, I think, in the beginning of this year. And it came with a very simple question. They presented multiple tables. We are not talking about singular table reasoning like a CSV spreadsheet, but we talk about multiple tables, like three to five tables. And they just handed over those tables to the large language models and asked them, okay, here are four options. What is the correct answer to a certain question? And as part of this data set, they had a lot of different sets of different tables. They used existing papers for that and their tables. So they had these different kinds of tables of different topics, different sizes, and so on. And they also had different question types. They had row match, item select, and so on and so forth. So they didn't only test for like one specific question or one reasoning capability, but for various different ones, which made this data set perfect for our test as well, though we differed in how we tested the LLMs, which I will speak about in a few minutes. So that's the data set we used. But to address the first research question, how do we actually evaluate the LLM outputs? I mean, there are a bunch of classical methods like Sacre Bleu or bird score, but just to start out with a very simple example, if you have a question over a table of like the World Cup of football, then you could ask a question like, how long has the team that qualified for the 1999 FIFA Confederations Cup in June existed? And then you have two answers. One is wrong, one is right. But the question is, do those scores actually provide valid outputs, like the Sacre Bleu score and the bird score? And in both cases, like, higher is better here. We already see that in the bird score, they are roughly the same, so it's hard to differentiate between the correct and wrong answer. And for the Sacre Bleu score, for the specific example, it's actually the wrong way around. The correct answer has a lower score, and the false answer has the higher score. But why does that happen? And is that a large-scale problem? So to start out with the Sacre Bleu score, what is the Sacre Bleu score? it just measures the similarity between two texts. It does so by using the n-gram overlap between two texts, and also introduces a brevity penalty. And what you see here is one example just to illustrate that. You have a reference and you have a candidate, and those two texts are compared with each other. And the reference is the correct text, and the candidate is another text that is to be evaluated. And what you can see here is like there's not a specific count, but the candidate text and reference text, they are very close, only with one difference. And the candidate text, the cat is not on the table, but below the table. But because the Sacre Bleu score only measures how similar the text is in general, it still assigns a very high score to those two texts, even though they are logically wrong. Like there's a error in the response. But the issue also exists the other way around when it comes to tabular data specifically, because with tabular data, if you evaluate the tabular reasoning capabilities, the answer might, like your ground truth, which you compare against, might just be a single number, which is like 196 centimeters, for example. But the LLM might generate an output like the person is 196 centimeters tall, which is a very long sentence, because that's what large language models are trained to do, or trained to output. And if you use the Sacre Bleu, all of those other words around it, they are like not part of the ground truth, and therefore the Sacre Bleu produces a very low score, which, even though that is like technically what you want to see as an output. So that's just very unreliable. And even if you force the LLM to produce a very small output that's very much aligned with the reference value, then you might end up in a situation where the LLM outputs something like, okay, not in centimeters, but in meters, and goes to the person is like 196 meters tall, which in this case still produces a very low score because they are not very much aligned with the reference, even though they logically mean the same thing. So that's like the theoretical issue with Sacre Bleu, but we also measured that with the data set that we used. And what we were able to see that, yes, indeed, we labeled a bunch of answers ourselves, so we knew whether the LLM-generated answers are correct or incorrect. And we just see that on the right side here, that the score distribution, they overlap to a vast degree. Like it's very hard to differentiate between correct and incorrect answers. And that's just a huge issue, because this metric is still used in a lot of papers. But obviously for these tabular reasoning tasks, like Sacre Bleu specifically, is insufficient. And we see a similar pattern with BERT score. BERT score compared to Sacre Bleu compares the embedding representation. So it uses a deep, like an embedding model for embedding those texts into a vector, and then computes the similarity between the output and target vectors. And what happens here again, it's pretty much the same story. You convert the reference into an embedding vector, and you convert the candidate into an embedding vector, but just because one word is different, the vectors look similar. Like in this case, the difference should be a bit larger than with Sacre Bleu, because the like below and on should be somewhat of a difference in the embedding space, but still, in general, the BERT score will be quite high, even though the answer like technically might be wrong compared to the ground truth. And the same story again, if you like, or slightly different one, if the LLM produces a slightly wrong answer, like in this case, it just says, okay, it's 194 centimeters, then the embedding representation for 196 or 194, those are very, very similar. So again, the BERT score produces a very high score, even though technically the answer is incorrect. And that's incredibly important for tabular reasoning capabilities because you want your answer to be correct. You don't want just to have a guess. You don't want it to be like nearly correct. But in most situations where you work with tabular data in companies and whatever other settings, you want your answer to be 100% correct. And again, BERT score doesn't deliver there. And like we did with Sacre Bleu, the score distribution between the correct and incorrect answers overlap to a very, very large degree. Like it's very hard to differentiate between the correct and incorrect answers, like you can see here on the right side. So what did we do instead? Like all those classic metrics, they apparently don't work. So we had to go with a different approach. And we went with an LLM as a judge. So there are a lot of papers that already used LLM as a judge, and there are scenarios where it works and where it doesn't. But in our case, we went with an LLM as a judge because it meant that we could ask the LLM open form answers. We didn't have to go and force it to a specific format like other benchmarks did. We could just use it the way most users would use the large language models. And the other big advantages are that the judges then don't look at just an embedding representation, but they actually look at the correctness beyond the surface level text. They check whether the specific number that is returned by the large language model is actually the ground truth number that is to be expected. And it's also just format tolerant. Like I said, it's not important how the answer is phrased specifically, only whether the ground truth matches. And how we use that is you see the prompt on the right side, the prompt you used for the judge. So when it comes to the following question, and then there was the question, does the answer match the expected response value? And we knew the ground truth from the data set provided by TQA bench. So we simply could use this prompt, and maybe as a background information for that test, we used the Gwen 2.5 model with, I think, 30 billion parameters. And obviously we also tested that, and on our 300 human labeled correct and incorrect responses. And we saw that the LLM as a judge is actually very well aligned with our own labeled data. So it's not a 100% match, but it's much better than the Sacre Bleu and BERT score. So we decided to proceed with that as an accuracy metric, whether the answers are accurate or not. So yeah, now that we have this method of checking whether the answers of the LLM as a judge, whether the answers of the LLMs over tabular data is actually correct, we went ahead and tested a bunch of LLMs. How robust are they against tabular data? How correct are they in their ability to answer questions? And for that, compared to the TQA bench that I introduced earlier, we switched to an open question setup. Like I said, because we had this LLM as a judge, we didn't have to enforce a certain structure. We could just use the prompt on the right side, where we just ask the question and like put some extra prompt to that. But like I said, we didn't have to force it to a specific format. And what's also important to note here is that we just handed over those different tables, like most of the times, like 3 to 5 tables. We just handed them over as part of the prompt. We didn't do like any fancy formatting there. And yeah, we also extended the TQA bench data set with a missing value and duplicates test, which was very important because that's also something we see in real world data a lot, that they are just values missing from the tables and they are duplicates. And what was also very nice about the TQA bench data set is that they provide a function to scale the tables to different token limits, like the scales you will later see on our plots. Those are how many tokens those tables used up in our context window, but without breaking foreign key relations. So we were able to also test how the reasoning capabilities scale in terms of table size. So yeah, what did we find? For example, I just brought two examples. First, the subtraction task, like what is the average delay of Pittman Airlines? And what we see here is that the performance of those models in general is not great. We see a very significant decrease with scale, but what is important to point out here is that even at the smallest scale, like 1024 tokens, which is not that much, like that's a very reasonable table size, the performance of these models are not great. As a side note, in terms of parameter size, we always use the 7 or 8 billion parameter models of these models, so they are quite small, but we also see them being used in, for example, retrieval augmented generation setups a lot. So I think that's still quite realistic. But what's also important to note here is that on the right side, we actually included the results from the TQA bench. And what we see here is that using those 4 options, because TQA bench always provides 4 options, they ask the model, hey, you have these 4 options available, pick the right one. This actually overestimates the performance of these different LLMs quite significantly, because what you have to keep in mind here is that if you provide 4 different options, the chance level is actually 25%. So like all of these performances, you could never see with TQA bench just because the chance level is 25%. And yeah, so having a proper evaluation metric is very important if you evaluate those reasoning capabilities of LLMs over tabular data. And just to show one other example is the average task, like what is the average height of USA actors, and then you have very long lists of these actors and their heights and so on. And what we see here is, again, the performance just falling off a cliff beyond a certain table size. But even at the smallest table size, the performance is still quite mediocre. But I also chose this example because this is like the only outlier we had, that GPT-4o Mini for the average task actually is quite stable. With all other tests that we performed, the performance just dropped off very significantly, always for all models. This is the only outlier that we encountered, and we couldn't even completely explain it ourselves because we looked at the outputs and there was nothing suspicious in there, but for some reasons they remained remarkably stable here. But yeah, beyond that, in all tests that we performed, the models drop off quite significantly. And again, here you see the Gren 2.5 performance and TQA bench, but also the Gren 2.5 performance in red in our test. And again, the TQA bench just very much overestimates the performance by providing those 4 different options. And yeah, but what happens if you apply like common table data perturbations, like missing values, column shuffling, duplications, like all things that we see on a day-to-day basis in companies and all kinds of settings? There are just sometimes values missing from the tables. And like, to give an example, what we mean by that is, for example, if the original is a list of flight delays, then if you ask for the average here, the ground truth is 2 because it's 6 plus 2 plus 0, 6 divided by 3 is 2. But then if you take out one value in the middle, then the ground truth becomes 1. And we also updated the ground truth. So we recalculated the ground truth, taking those missing values into account before we handed over those tables with the missing values to the large language models. And what's interesting to see here is that we didn't only ask the models for the correct answer, but what we also wanted to see is whether the large language models actually acknowledge that there's a missing value. Because ideally, what you want to have is, from our perspective, not only the correct answer, but you also want to check whether the large language model acknowledges that, hey, there's a value missing from the table. Be careful with that result because that might have an influence depending on the task. So we tested for both of these cases. And what we see is that the accuracy by and large remains remarkably stable. There are a few outliers, like for example, Gran 2.5 for the entity lookup tasks with missing values had a slightly better accuracy for whatever reason, but that's probably largely due to background noise because these values are so low that, yeah, you just introduce a lot of noise in there. And same for the sum task, only this time the other way around, where the performance actually decreased, but it's from 16 to 8%. Like at this point, it can just be considered noise in our results. And beyond that, it remained remarkably stable. But still, on the acknowledgement side, in only 50% of cases, roughly, the large language models actually acknowledge that there are values missing from the table, which again is by far not good enough for any real-world applications because that's just a coin toss. Yeah, so even though it's better than what we expected originally, it's still by far not good enough. And same goes for duplicates. For duplicates, what we wanted to see is, again, does the LLM acknowledge that there are duplicates, and how does it handle these duplicate rows? Ideally, it would just ignore them because that's what you usually would want to do with duplicates. And what we saw here is actually that, like on average, the performance decreased quite significantly. Quen 2.5 being the outlier again, but the average of the performance dropped quite significantly compared to the baseline. And what was even more problematic, that in most cases, those large language models didn't acknowledge that there was a duplicate within the data set. Llama 3.1 did a little bit better here, but it's still far away from what you would want to see in a test like that. Yeah, and in conclusion, answering like the first research question, we showed that traditional text metrics are just not fit for evaluating the responses of large language models for analytical queries over tabular data. Like the score distribution, they just overlap so heavily that that just fundamentally doesn't work. But we also showed that for our tasks, the LLM-as-a-judge approach is actually pretty well aligned with the human-labeled evaluation. Using that technique, like the LLM-as-a-judge, we then were also able to show that LLMs do struggle very significantly with reasoning over tabular data at realistic scales, and they also don't often acknowledge if there are common data perturbations, such as missing values and duplicates. So where does that leave us? I mean, first of all, I think there's a lot of work to be done at strengthening the reasoning capabilities of large language models over tabular data. But also what we didn't cover in that paper, and I think this is also something that's a great point for discussion, is we didn't evaluate the effectiveness of existing solutions. I mean, we all like have heard or are working with MCP servers by now, making the entire thing a bit more interactive, giving the large language model access to a Python environment so that it can use pandas for like interacting with tables, and also what better prompting might achieve here. So there's a lot of interesting future work to be done on that topic. But yes, with that, like time-wise, that's perfect. And yeah, with that, I think we can go over to the discussion part and like any questions. I mean, I already see a bunch of questions in the chat, but yeah.
Awesome. Thanks so much, Cornelius. That was super awesome. Yeah, there are a lot of questions already. So I see Daryl, you've been using the Q&A. Thank you. I just asked you to unmute. Feel free to maybe ask a couple of your questions, and then we can get back to the other ones
Yes.
afterwards.
Thank you, Raj and Cornelius. So thank you for the paper and thank you for your hard work. I've been using, well, not using, but applying your paper onto a case study I've been working on with an AI agent on a operating system, Windows 11, open up Microsoft Excel, not through the web, but having it be like a co-pilot for myself. How can LLMs or small language models be able to understand the between capability and reliability between data itself?
You mean like US, like I'm working under DS just to get to see if I get the question right. You mean you're working under the assumption that the small language models are able to understand the data? How capable are they at assessing how reliable this data is, or what was like?
More like the understanding of the LLM doesn't have experience with that data, like we human beings do it as coworkers or colleagues. We get trained on that data. We understand. We experience that data day by day. How can the LLM or small language model be able to differentiate that between its true understanding right now with the real world data?
I mean, I think that's a very interesting question that we also try to cover a lot in our research, because if you look at tabular data in general, you just need context. If you look at most companies' databases, if you don't have context to certain column names and so on, it's very hard for any kind of model to make sense of the data, because it's just lacking the necessary information to understand that. So I don't think there's a definitive answer to that yet. I think when it comes to LLM specifically, just you can improve the situation by just trying to provide as much context to the tabular data on your, like that you show to the large language model as possible. But I think in general, that's a very open question to like, what kind of context do you need? How do you ensure that the models are actually aware that they need more context to solve a task accurately? Like that's, I don't think I have a better answer to this at the moment. Just saying that this is like still a very open question in academia, from my perspective.
Understand and thank you. Raj, so I have like 5 questions. Do you want to switch out between other people?
Yeah, that would be
Okay.
great.
Okay,
I'll
cool,
go
cool.
ahead. Yeah, let's see. So in the chat we have Lakshya. Let me. Are you? Oh, it looks like Lakshya might not be here anymore. But yeah. So Lakshaya's first question was, how would the LLM reasoning over tables be impacted without schema linking? That is when you don't filter tables yourself, but raw dump a huge set of tables.
So, I mean, schema. The honest answer is how the performance is impacted by schema linking. We don't completely know. That's something that's still up for future research to test the impact of all these techniques that have been around. But what schema linking and so on have been used mostly, as far as I know, is in the context of, okay, you also provide additional tools to make sense of different tables. But yeah, evaluating those systematically is something that would be very interesting to see in upcoming research.
Awesome. Matan?
Yeah, hi. Can you hear me?
Yeah.
Yep.
Yeah, so I wanted to ask if like if you first create sentences from the table rows according to a relationship between the column names, does performance on reasoning test improve?
You mean like, can you like explain what you mean in detail by linking the different columns?
Yeah, because LLMs work basically, they were trained on on large groups of text. So it might look a bit ad hoc, to do it, but I just wonder if you first take a table and you describe like as an initial step, and then you describe a relationship between the column names, and then you just change it to sentences, okay? And then you ask a question about it. It might help the LLM use. It might bring it closer to data it was trained on, and maybe it'll be easier for it to kick in any reasoning abilities.
Now I understand the question. Thank you. Yes, it might. You're right. Like using the column names to like bringing it closer to the training data might improve things. But I think what is still a big issue here is that the contents of the tables are still like just show up as a very long string to the large language model. And I think what's happening a lot under the hood is not that the column names in itself are the issue, but just if tables get too large in terms of length, the LLMs like start losing track over in which column they are at any given moment and just lose track over all of these different rows, what exactly they should be looking at. Because large language models, like you said, are only trained on text. So it might improve performance a little bit just because you're getting closer to the original data distribution. But I think the largest issue there then still remains that, the data in itself is just very, very large and hard to comprehend for the large language model.
Yeah, but you don't have to start with really large tables. You can just start with small tables as a POC to even check if it helps in any way. And then if you find it any significant result there, you can try and parse the table in a different way that maybe doesn't create very large sentences, but add dots, add connectives, parses it in a way that can. What I'm saying is that it's two different questions. The first question, can it help to do some pre-processing on the table data before you give to an LLM, is one question, and then how can I elongate the effect if I have a larger table or bed names or stuff like that. It's just two different things, I think.
What we know from existing research is that like table formatting does have an impact, just the way you like turn the table into a string does make a difference if you use just like these classic pandas data frame to string methods, or if you use CSV or JSON or Markdown. Yes, that does make a significant performance impact. We just went with the most basic CSV encoding because, like I said in the beginning, I think that's what's like most realistic, how users use that at the moment. But yeah, to answer your question, yes, that does have a significant impact on the performance. And to the second question, how I hope I remember correctly, how to mitigate these like very long tables and how to make it scale up basically. I think there are a lot of techniques on approaching that, like chunking it up, but you always have the issue that for some answers you need the entire table inside of the context window, or you need to have access to the entire table, whether you solve that by using pandas and the LLM never actually sees the table it's working with, it just sees the columns and like a pandas Python interface. That's an interesting question, but that's also something that's yet to be evaluated.
But you're saying that the main parsing method is just table to text or something like that. It's not like they swap the tabs for connectives, like I don't know, like relational words or something that is what do you say? That gets its meaning from the relationship between the column names.
I mean that's what we use. We use just basically table to text, but like I said, it's hard to just eyeball the effect of any other encodings there. But yes, that this could be a valid approach at improving the performance. I would be very curious to see any results on an approach like that.
Thank you.
Thanks for your question.
I think somewhat similar. There's a discussion going on in the chat with Lakshya and Jinyang. I think Jinyang, I'll ask you to unmute.
Hello. I wasn't exactly expecting to be talking, but I can ask my question. So I don't quite understand this part where you convert the table to text, because I know like for sure there exists this tab PFN which does this cross attention on a much lower level. So it does encode like the actual columns and rows of the table into the attention mechanism. So it seems kind of noisy that you have to first convert to this intermediate representation, which is your raw text, and then, you know, get the LLM to reason about it.
Yeah. Yeah, you're actually perfectly right about that. And I think that's, maybe I didn't make this clear enough in the beginning. What we were saying in this paper is not that this is a very good idea to do, but that we just wanted to test how well it actually performs. And I, like, personally, I'm also of the opinion that this performance can be increased by, or like these gaps can be addressed by changes to the attention mechanism in the future, TAP-EFN with its cross attention being a very good example, even though like you have to be careful of the limitations of TAP-EFN, because TAP-EFN doesn't provide like a natural language interface. You can't just prompt open questions, which I think is what made ChatGPT and so on so great and easy to use for users, is that they can just interact with it via text. So TAP-EFN like performs amazing work in the predictive ML domain and so on. But I think TAP-EFN is like a lot harder to use for the average consumer. But yeah, to answer basically the point that you are making, yes, I totally agree with you. Like there are very interesting approaches, and TAP-EFN providing one very interesting like addition to the attention mechanism there to make like improve understanding of tabular data.
Thank you for the answer.
Yeah, thanks for the comments.
Awesome. Manuel is asking, why do we even allow fractional nearly correct answers, or did that not apply to LLM judges? In general, the answer to some question is a result of some deterministic execution path plus a bit of interpreting it.
No, like for the LLM-as-a-judge, we didn't allow like nearly correct answers. I just wanted to give that as an example why the BERT score is not working here, because like these fractional answers, like these nearly correct answers, they create very similar embeddings, so very high scores, and meaning that BERT score even like doesn't provide a good metric here. But for the LLM-as-a-judge, we prompted it in a way that only like this one correct example should be deemed correct. And like if it's nearly correct, like it's still wrong. That was actually exactly the reason why we switched over to an LLM-as-a-judge.
That makes sense. Daryl, I know you had a few more questions, so feel free.
Yes, you guys just answered my question about the object permanence in regards to large language models. So I'm not going to ask about that. The question is, how can large language models overcome long horizon tasks when it comes to tabular data? Meaning, we're going to be using them in the near future as collaborators. How can they sustain the capabilities as we do with memory and experience and so forth with that data itself?
I mean, that's I think the third time I say this today, but that's also an unsolved question. I think a lot of the necessary context, like the best option you have at the moment, is try to update the context that you provide in the context window of the large language model regularly, like if something changes of the underlying data, or there's new insights, or you just have new patterns, or something changes within the companies or the collaborators, you just try to update the context like that you provide to the large language model. I think that's honest, like from my understanding, that's the best approach you could have at the moment, because like fine-tuning or building laws of your LLM for like these day-to-day updates is, I think, not practical. So yeah, I think at the moment just updating the context that you provide in the context window to the large language model is probably